Hello everyone, welcome to the second episode of Math-Adda. I'm your host Shankhadeep and we have a guest today, Dr. Ashwini Dasgupta, who is the founder director of Chintaganit Kendra and a researcher, academician, doctorate from University of Wisconsin-Madison. He works on group
Milwaukee,
theory
actually.
with Wisconsin, Milwaukee. Welcome Ashwini.
Thank you, Shankhadeep. It has been a pleasure to be with you in this Math-Adda. I saw the first episode. It was really nice.
Yeah, we actually got very good feedback for the first episode. So thanks for all the love. And as you know, in the first episode, I told you, we will take Olympiad problems as conversation starters. The conversation need not be limited to the Olympiad problem, but let's start with something. Actually, we have a very nice problem today. This is from INMO 1987.
Yeah, I can see the problem now. Yeah,
So, Ashwini, does this remind you of something?
yeah. Of course, it reminds us of the Fermat's last theorem, the celebrated Fermat's last theorem, which Andrew Wiles, I think, solved. Right. Uh,
Yes, it did.
there is one thing. So one thing whenever I think about this problem, um, there is an anecdote that I'm reminded of. That usually mathematicians work in a group, or maybe there is at least a couple of people they are talking to. But I don't know whether this is correct or not. But I heard that Andrew Wiles sort of worked solo for over a decade on this single problem. It is quite phenomenal in that sense. And then sort of came up with the entire solution. It's remarkable in many sense, many layers. But of course, this solo journey of a lone shark, learning different tools and trying to solve a single problem in a single-minded manner, I found it quite intriguing at that early age when I heard
Very,
about it.
very inspiring as well.
Yeah,
We will talk a little bit about the problem, but first
yeah,
tell me one thing. If you were a student writing the exam,
yeah.
would you have used the famous last theorem?
Of course, not in 1987. It was not used
Yes.
at that.
Yes. So the theorem was proved, if I'm not wrong, in
Uh-huh.
1994. So in
Yeah, something like
1987,
that.
yeah,
In
so
90s, yeah.
yes, so in 1987 it was still an unsolved problem. Okay, so
Right,
nobody
right,
could have
right.
written by famous last theorem this holds. And by the way, if you get a similar problem next year in the INMO or RMO,
Yeah.
don't try that, okay? That it follows from
No.
famous last theorem because you are not going to get any marks for that.
Yeah, probably they will put a footnote. Don't use Fermat's last theorem because it's a highly non-trivial theorem in number theory. But yeah,
Anyway,
certainly not elementary. Certainly not elementary.
certainly not elementary.
Yeah.
Anyway, let's talk a little bit about the theorem. So this theorem was proposed by a French mathematician called Pierre de Fermat.
Wow. That's
Yeah, I speak a little bit of French.
yeah, and a little bit of Portuguese. I mean, a lot of Portuguese. I know that because let me tell the viewers, Shankodeep actually translated a couple of books from Portuguese to English. Is that right? Or English to
Yes,
Portuguese? Which
two
way was
books,
it?
Portuguese to
Two
English.
books. Okay, okay. So he has a flair for languages, apart from other things. Yeah.
So this guy, he also had an inspiring life. He started doing mathematics after he was 40, and it was a
Oh,
part-time thing for him. He had a job, a government job, and just to pass his time, he used to do some mathematics. And he had a habit of jotting down stuff on the margin of books. One book specifically, I think it's called Disquisitions, and it's a Latin
This
book.
question,
That
yeah,
yeah,
yeah.
that's something that I don't know how to pronounce.
This
This
question is the arithmetic or something like that.
yeah,
I think
something.
it was a Greek book
No, it was
which
Latin.
was, oh, it was translated into Latin, maybe, I don't
Yeah.
know. It was written by Diophantus, is that right?
Yes, yes. So
Uh,
this guy used to write stuff on the margins. Sometimes
right,
there were
right.
proofs, sometimes there were
Uh,
no proofs. And
right.
then one day, in one margin, he wrote something like, "I have, I have discovered that x power n plus y power n is equal to z power n has no solutions in positive integers when n is greater than 2." He also wrote that I have found a truly remarkable proof for this result, but this margin is too small to contain it. And
Yeah.
he didn't leave the proof anywhere else in his work. And
Uh,
people suffered for centuries, 3 centuries, in fact, more than 3 centuries, to find that proof. And nobody could find a proof.
uh,
And it was proved finally by Andrew Wiles in 1994, if I'm not wrong. And it actually, the struggle to solve this actually gave birth to serious areas of research in mathematics, entirely new directions that were developed just to tackle this problem. Many
right,
mathematicians were unable to solve this, but ended up solving other things. Okay, so
right,
this is one of the most important and most famous problems in the history of mathematics.
right, right.
And actually, when as Oshani was telling us that he did this almost alone. Alone means he used tools that were developed by other mathematicians, but he used to work alone mostly. And first time when he published, he instantly became a celebrity because nobody was
Right.
working on this. Nobody thought this was possible. And he, by celebrity, I don't mean that he became a celebrity in the mathematical community. He became a general celebrity. He was approached to sponsor stuff, to appear in ads and stuff like that. And he was,
Oh,
and he was once asked to be a model for
oh,
jean pants for a popular brand, and he said no. And there's a joke in the mathematical community. There could be some truth to it. I'm not sure that he declined the offer because the name of the brand was Gap. Okay. See, this part is true. This part is true that he was approached by Gap to be a model, but I don't know if he actually declined the offer for this reason.
uh,
Okay, so
one thing I suddenly I read it somewhere that about Pharma, or I don't know the exact pronunciation, but uh, he had an excellent collaborator called Marcin. So
hmm,
uh, because a lot of work that he did, Pharma did, involved a lot of calculations, which was impossible to do without, I mean, very hard to do without a calculator or a computer, which was, of course, not available at that point of time. And Marcin, who was, I think, a priest by profession or something like
yes,
that, he he had this interest in calculating very complicated, long and windy calculations and so on. So Marcin used to collaborate with Pharma, and a lot of great mathematics came out of it. But anyway, yeah, continuing.
actually, there are many such fascinating stories that you can find in a book called Men of Mathematics. It
Acha.
by E.T. Bell. I shall
Okay.
leave a link to this in the description. Okay.
Awesome. Yeah, sure.
Okay, let's continue our discussion. There are many special cases which are somewhat easy to prove. For example, a not special case, let's call it case number 0, is that where n equal to 2,
Mm-hmm.
then the equation is just x square plus y square equal to z square, which clearly
Right.
has many, many solutions. And in
Right.
fact, if you're given one solution, you can produce infinitely many. If
Right.
you are given 3 square plus 4 square is equal to 5 square,
Uh-huh.
then 3r square plus 4r square is equal to 5r square for every integer r.
Mm-hmm.
Okay, so starting from any one, you can find infinitely many. And when these numbers are relatively prime, such a triple is called a primitive solution. Actually, three numbers x, y, and z that satisfy this are called a Pythagorean triple.
In fact, as we were discussing a few moments ago, just before when we were talking about this, making this Math-Adda, one interesting but easy problem could be like this: that one can show that if GCD of x, y, and z is equal to 1, then they are in fact pairwise co-prime. That means GCD of this would imply that GCD of xy is 1 and so on, like yz is 1 and so on, which could be an useful result for many purpose of many problems. Yeah.
So x, y, z is called a Pythagorean triple, and when that happens, when they're co-prime,
Right.
then they're called a primitive Pythagorean triple.
Right.
And when that happens, when they are indeed primitive, then there is a formula which goes like this. There are integers p and q co-prime such that z is equal to p square plus q square,
Right.
y is equal to 2pq, and
Right.
x is equal to p square minus q square. Clearly, this order does not matter. You could take y
Yeah.
equal to p square minus q square and x equal to 2pq as well. Doesn't really matter. The triple remains the same.
Right. Right.
Fine. So this is a basic case, basic non-case in fact, because the theorem actually does not talk about n greater than 2. And Oshami, have you seen any other special cases of this theorem
Yeah, I
except
mean,
for this
I
one?
saw the n equal to 4 case actually. I think I saw it first time in Burton, or maybe it was in the book of Arthur Angel, Problem Solving Strategies, where maybe I can discuss it a little bit. For n equals to 4, that means we would like to show that x to the power 4 plus y to the power 4 equal to z to the power 4 has no solutions. So, has no integer solutions. Positive integer solutions, I mean integer solutions. This case, I think I first saw it in Arthur Angel actually. They were discussing a very interesting topic called infinite descent, and maybe we can talk about it a little bit in this particular video. And of course, using this method of infinite descent, Fermat proved that in this particular case, there is no integer solution. Fermat did not directly prove this sub case. He proved another rather geometrically looking statement, but that would directly imply this one. So let's say Fermat proved this. So the way it goes is like this. So uh, we would show that x to the power 4 plus y to the power 4 equal to z square has no solution. Whenever I say has no solution, please understand that we are talking about integer solutions. Now, why is it sufficient to show this? Because of course, if there is a solution for this particular equation, then simply by putting z equal to z square or something like that, we would be able to find a solution of this case, right? So if we can show that there is no solution for this case, then it would automatically prove that there is no solution for the prior case. It's a much stronger statement in some sense. So how do we go about it? Well, observe that x square y square z forms a Pythagorean triple. In fact, we could say that it forms a Pythagorean primitive, because if there were certain things which are common, like if there is a GCD of x square, y square and z, we could just pull it out and cancel it off. So we can concentrate on the case where it's a primitive triple. I'll remind you that means that GCD of x square, y square, z is equal to 1. But it also means that the pairwise GCD, which I pointed out a few moments earlier, that the pairwise GCD is also 1. So we will be using all of these facts. Now, now let's use the thing that Shankhodit talked about a few moments ago. There is a representation, a parametrization of these of this particular Pythagorean triple, and it goes like this: that you can find P and Q. Let me change the color. There is P comma Q, where GCD of P and Q is 1, such that x square is equal to P square minus Q square, y square equals to 2pq, and z square equals to p square plus q square. Oops, made a mistake. Z is equals to p square plus q square, because x square, y square and z is a Pythagorean primitive. Okay, so we already noticed that something very interesting has happened. If we scroll down a little bit, x square equals to p square minus q square, this particular thing, if we rearrange it, we automatically get x square plus q square equal to p square, right? That is again a Pythagorean triple. Is it a Pythagorean primitive? Is it a primitive? Is the GCD of x, p and q equal to 1? So that is something that you can check. If it is not 1, does it affect the previous hypothesis that we have made? But for the moment, we will consider, we hope that you understand that it's a primitive, and we will proceed by the representation of this Pythagorean triple one more time. So here x is equals to, let's say, some m square minus n square, q is equals to 2mn, and p is equals to m square plus n square, right? Okay, so now we will do one interesting thing. Notice that earlier we found that y square equals to 2pq, right? We found that already. And we have a representation of q and p here. So let's use all of these together. So we have y square is equals to 2 times p. P is m square plus n square. And q is 2mn. That's what we have. So we have y square equals to 4mn times m square plus n square. So a couple of things you have to realize down here. First of all, since p and q have GCD 1, remember in a Pythagorean triple, they are pair primitive, they are pairwise co-prime. So p and q have GCD 1. So in fact, 2mn and m square plus n square have GCD 1, which would mean mn and m square plus n square have GCD 1. Okay, so that is one of the results that we will use. The other result is that you can actually get rid of this 4. Why? So look, the right hand side is even, which means y square is an even. So basically y is even. So you can write this as, let me change the color. Let's use this one. So 2y prime, because y is even, I can write it as 2y prime. So 2y prime square equals to 4mn times m square plus n square. So 4y prime whole square equal to 4mn m square plus n square. 4 cancels. So y prime square equal to mn times m square plus n square. Now notice that we already found that mn and m square plus n square has GCD 1. Which means we have two co-prime numbers whose GCD is, or whose product is a perfect square. Two numbers mn and m square plus n square whose GCD is 1, their product is a perfect square. How can that be possible? Well, that can only be possible if each of them is a perfect square. You can think a little bit about this and give me a rigorous sort of proof of that fact in the comment if you can. So each of them is a perfect square, which essentially means that m square plus n square equal to some, let's say, capital T whole square. But wait, we also know that mn is a perfect square and GCD of mn is 1. Mn is a perfect square, some alpha square say, and GCD of mn is 1, which means again each of m and n is a perfect square. So m is some m1 square, n is some n1 square. So let me replace it here. m1 square whole square plus n1 square whole square equals to t square, which means m1 to the power 4 plus n1 to the power 4 equal to t square. So Shankadeep, could you tell me what just happened? We just started off with x to the power 4 plus y to the power 4 equal to z square and ended up with something like this. What goes wrong? What do you think? I mean, you've seen this sort of thing before. Could you?
Yeah. Yeah, the thing is, we are trying to go down a staircase which is finite. So there has to be a last stair. Okay. So
Right.
there will be a point of time when we won't be able to go down anymore. Is that
Exactly.
making sense?
So
I don't know. Okay.
yeah, exactly. So basically, what we found here is that if you make the set of all numbers, like say alpha square, beta square, t square, z square, all numbers which can be written as the sum of two fourth powers. If you take all such numbers which can be written as sum of two fourth powers and put them in a set, all square numbers which can be written as sum of two fourth powers and put them in a set, that set contains only positive numbers. So there has to be some last number or the smallest number in the set. This is by well ordering principle if you want to be too technical. But even if you don't want to be too technical, if you think about it closely, if you take all square numbers which can be written as sum of two fourth powers, there has to be a smallest one in that set because those are positive quantities. So if a set of positive numbers has the smallest number in the set, any set of positive numbers. Now, what we essentially did is we started off with one such member of the set, of this set, and produced another member which is smaller than this one. And you can sort of think about an argument why to essentially produce smaller than z square, why t square has to be smaller than z square. And we can do this over and over again. Now that we have another n1 raised to the power 4 plus n1 raised to the power 4 equal to t square, we have another one, another triple like this. We can do it again, this entire process again, to produce an even smaller square number which can be written as sum of two fourth powers, and do that again and again, so infinitely many times. So that is like an infinite descent. You go down, go down, go down, but you cannot infinitely go down because there has to be a smallest number in the set. So that is literally the infinite descent, that strategy. It has been used in other problems as well. So this was Fermat's strategy, you can say, quite ingenious I must say, which shows that for n equals to 4, Fermat's last theorem is a done deal. So, but Shankadeep, what can we do about the problem from INMO?
Yeah, we are going to go to that, but before that, I would like to make a remark. It is possible to do this problem without writing so much about infinite descent. Just say, suppose there are solutions, we take the solution with the least z and we produce another one with a smaller z. So that z was not the least.
Yeah,
It's almost identical. The argument is almost the same, but you write less. You don't have to say, hey, I produce this one, from here I produce a smaller one.
So it's like a proof by, then it would be like a proof by contradiction. You started with the smallest square quantity and then you produce a smaller one. Yeah.
Okay, so there is to you it might seem to be identical, but there is a subtle difference. Okay, think about it. Fine, let us go back to the actual problem, which is which can be a bit anticlimactic after this beautiful proof. So this says x power n plus y power n equal to z power n has no solutions if n is greater than or equal to z. Okay. And this can seem a bit difficult because there is no limit on the coefficients. The coefficient can be as big as z, but have patience.
You mean the power, right?
Yes. Sorry, the exponent. The exponent could get very large, but let's see. So clearly, z is the largest in the triple, right? Z is greater than x and greater than y. So z is greater than x and z is greater than y. It means z minus 1 is greater than equal to x and z minus 1 is greater than equal to y. It's because we are working with integers. That's why. Which means z minus 1 power n is greater than equal to x power n. Now we add the two inequalities and we get 2z minus 1 power n is
Mm-hmm.
greater than equal to x power n plus y power n,
Mm-hmm.
which is z power n.
Right.
And that gives us 2 is greater than equal to
Z over Z minus 1 raised to the power n. Yeah. Oh, I see. Ah, yeah, of course.
right?
Right.
Now we can expand this by the binomial theorem and get,
Okay.
sorry, I will have to change the place a little bit. We can expand this by the binomial theorem and write 1 plus n by z minus 1
Mm-hmm.
plus n choose 2 times uh, 1 by z minus 1 square
Mm-hmm.
plus stuff. Okay, everything here is positive.
Right.
So this whole thing is greater than 1 plus n by z minus 1.
Mm-hmm.
And n is greater than equal to z. So this is greater than 1 plus
Mm-hmm.
z by z minus 1, which
Right.
is greater than 2.
Right. Because Z by Z minus 1 is of course greater than 1. Yeah. So that's a contradiction. Fantastic.
Yeah, so you get 2 is greater than equal to 2. Now 2 is, if you get 2 is greater than 2, which
V2
is
is
clear,
greater than 2, which is
which is clearly a contradiction.
looks like a contradiction.
So this was it. It did not really involve any number theory. So
This is really
there can be many fun special cases you can come up with. There can be, you can maybe put restrictions on the exponent like we did. We took n equal to 4 and then n equal to 2, then we took n greater than equal to z. There can be many
yeah.
more, and there can be other more innovative restrictions, and they could lead to nice proofs. So if you know any such proof, please let us know in the comments. And I
Yeah.
think we are going to stop today. We are going to
Yeah.
stop. Thank you, Ashwini, for your participation.
Thank you, Shankadi, for this wonderful session. Thank you. It is really nice.
And please let us know in the comments if you have any suggestions for future episodes, and also if you would like to participate, because this is an adda, it is open for all. Okay, let's keep the conversation growing. Okay, bye bye. See ya.
Bye.